So hello and welcome to a new lecture on statistics. The scope of today's lecture is to introduce the geometric distribution. And we saw in previous lectures that a distribution can be described basically by a function that provides the number of times a certain outcome in a random experiment is obtained on average. And we saw that if we asked for the question of how many times a certain outcome is obtained in a random experiment on average, that this concept is closely related to the probability of the outcome in a certain random experiment. And today we are going to discuss the geometric distribution, which is again a very special distribution in the sense that it describes k successive independent trials until a certain result is obtained with probability p, which is usually called the success result. To get started, let's write down the geometric distribution, the law that the random variables actually follow on a geometric distribution. So basically we have some random variable x which follows a geometric distribution and with success probability p. And the associated probability law here is probability the random variable to be x equals to be k is means that we obtain k minus 1 times no success. So we have full probability minus the success probability to the power k minus 1, because we have k minus 1 times no success, and then for the case time we obtain the result that we declared as success with probability p. So here again we will basically look at the random experiment flip of a coin experiment flip of a coin, and we will say that the success probability p is 0.6. So it's not a fair coin because we don't have a success probability of 0.5, but the success is obtained with probability 0.6. And we will say that the success is defined as obtaining tails when we flip the coin. So the associated no success probability, so the one of obtaining heads, is obtained with a probability of 0.4. So let's work out a couple of random variable probabilities. P of x equals 1, so that means that we obtain tails for the first flip. So we flip the coin one time and immediately obtain tails. So basically we have 1 minus p, the no success probability with k being 1, so we have 1 minus 1, which is 0, times the probability of success, and the probability of success is 0.6. So here this is basically 1 times 0.6, which is of course 0.6. Then we have the probability of x being 2, so this time k is 2, so we have 1 minus p to the power 2 minus 1, which is 1 times p. So basically we have 0.4 times 0.6. And this is 0.24. Then let's look at the situation where we obtain tails for the third flip. So we have 1 minus p to the power 3 minus 1, so 2, times probability of success. So we have 0.4 to the power 2 times 0.6, which is 0.096. And then let's look also at the situation p of x equals 4. So we have this time a success for the fourth flip. So k is 4, so 4 minus 1 is 3, times probability of success, which is then 0.4 to the power 3 times 0.6. And for this result we actually obtain, for this probability we obtain 0.0384. And then let's look also at the example p of x equals 5, which is again 1 minus p to the power 4, k is 5 this time, times p, which is 0.4 to the power 4 times 0.6, and we obtain 0.01536. So with this we are basically ready to draw the associated probability mass function. And we saw that the probability mass function can basically be represented within y and x axis, and on the x-axis we have of course the random variables, and on the y-axis we have the associated probabilities. So in this particular case we looked at x being 1, 2, 3, 4 and 5, and we saw that x being 1 has the highest probability, so 0.6, which is basically somewhere here. Then for x being 2, we have 0.24. So this is 0.3. 0.24 must be somewhere here. X equals 3, we have almost 0.1. And then the last one, almost 0.4. And this one is very small probability, and so on and so forth. So what we see actually is that obtaining tails for the first flip is the outcome that is the most likely. And then probabilities are decreasing rapidly and approaching 0 as we go higher with random variables. And from an intuitive point of view, this is very clear because we have a non-fair coin here. And so it's most likely to obtain tails with a probability that is slightly higher than the one of obtaining heads. And so obtaining tails immediately has actually the highest probability. So this basically concludes the discussion on geometric distributions. If you need additional information or explanations, please leave a message in the comment section below. Like my video and subscribe to my channel if you don't want to miss future videos. And see you in the next video.